Welcome to your first concept video for Chem 106 Lab for the spring of 2021. Our first experiment that we're actually doing in the lab is going to be the isolation of copper from copper ore. Copper solid can be found in nature just as it is, but also an abundance of minerals or copper compounds are found in nature. And since copper is such a handy metal to work with, we frequently want it, so we have to purify it. We have to extract it from minerals, and this is one way of doing it. So to begin with, we are going to be given a copper ore, and the copper ore contains compounds like copper 2 carbonate or copper 2 hydroxide, but it also contains a variety of iron compounds and zinc compounds and silicon compounds like sand, things that we don't want to end up with in our purified copper. So the first thing we're going to do is take this, let's choose copper carbonate as our example. We're going to take this copper carbonate and we're going to add nitric acid to it. And when we add nitric acid to it, we've got an acid-carbonate metathesis reaction. So an acid-carbonate metathesis reaction. And that means we're going to end up with carbon dioxide and water, the cation from the carbonate and the anion from the acid. The one we really care about, though, is right here, our copper 2+ that we got released from the copper carbonate. Now, there are other things that are going to be released as well, like some iron, some zinc. So we have to somehow manage to separate these substances from the copper 2+. So how are we going to do this? Well, we're going to add a little bit of base, a little bit of hydroxide. And when we tip it, the solution back basic, we're going to reform that copper 2 hydroxide. And by the way, iron 2 hydroxide, zinc 2 hydroxide, we're going to reform our hydroxides. Now, once you've reformed a hydroxide, you can actually add ammonia to it. And if it's a copper hydroxide compound, it will form this copper tetraamine complex ion very, very nicely. Okay? Very much forward reaction, very much favors these products. On the other hand, the zinc hydroxides and iron hydroxides and other such don't react at all with the ammonia. They don't react at all with the ammonia. So we can separate the two of these. See, the copper 2 hydroxide is a solid, as are these other metals. When you add the ammonia, that dissolves our copper hydroxide and creates this copper tetraamine complex ion, which is aqueous. So now I can filter. Up here I could filter to get rid of the sand. I forgot to mention that. Once you've dissolved everything the first time, and off goes the sand and whatever other junk didn't dissolve in your nitric acid. Here you end up with losing your iron 3+ and zincs and whatever else you had that stays as a solid. And now you have this copper tetraamine complex ion, which is aqueous. So after this, you have removed most of the contaminants. You've removed most of the contaminants. And you can isolate and purify the copper. So here we have our copper tetraamine complex ion, which is in equilibrium with the amine, with the ammonia and copper 2+. Now, that copper 2+ can grab a hold of some of the hydroxide, because we're still in a basic solution, to reform copper 2 hydroxide yet again. We keep coming back to that copper 2 hydroxide. Now, once we have isolated and cleaned up that copper 2 hydroxide, we can react it with a very small amount of concentrated sulfuric acid, forming copper 2 sulfate pentahydrate. And this is, of course, a hydrate. This is also a very beautiful royal blue crystal, and these are going to be crystals that we're going to let grow in our drawer over the course of the week, or not drawer, in a certain spot in lab. Then next week, we're going to use some zinc and some acid, and that zinc is going to reduce the copper 2 plus to give us just copper. So oxidation reduction reaction. Where the zinc reduced the copper 2 plus. Once you have reduced all the copper 2 plus, you can go ahead and filter it, dry it, and you've got your copper. Now, because we're doing this all very rapidly instead of over a period of time, we're not going to get nice looking crystals or a nice looking piece of metal out of this. You're going to get something that kind of looks like dark brown dust. But it's copper. Got to trust me on that. We're going to be doing a large number of things today. We're going to be dissolving an ore. We're going to be filtering off any gangue that remains. We're going to be changing that ore into a solid, and all the other tin, zinc, iron, whatever that have solidified as well. Then we're going to be taking the copper solid, and by adding ammonia, we're going to end up with a copper tetramine complex ion, which is aqueous. So then we can filter again, and now we've removed not just the sand and junk, which we did right away, but we've also removed the other metals so that our copper won't be contaminated with other metals. The next step is to go ahead and add some sulfuric acid to the solution and then let it sit so we can isolate this very nice copper 2 sulfate pentahydrate. Next week, we dissolve it in water. We use zinc and some sulfuric acid, and we end up with copper, reduced copper. Why do we use sulfuric acid as well? Why not just throw in zinc? It's a very interesting thing that happens here. Zinc reduces copper very, very nicely and very quickly. So if you add just zinc to the copper 2 plus by itself, you're going to end up with this core of zinc. And on top of that core of zinc will be your copper that will have been reduced out. So you'll end up with, effectively, pennies. You'll end up with copper with a zinc core. And that is very obviously impure, and we're trying to avoid that. So when we add the zinc, we add both zinc and sulfuric acid at the same time. What happens then is that the zinc itself reacts with the sulfuric acid, and we get zinc 2 plus, and we get some hydrogen gas and sulfate. We also have the zinc interacting with the copper and reducing the copper. And that's, of course, what we actually want. So why both of these? It's called a competing reaction. That zinc, which is not immediately reacting with the copper 2+, is immediately reacting with the sulfuric acid. This allows any extra zinc to be competed for by the sulfuric acid and the copper 2+. The sulfuric acid nabs whatever zinc isn't busy playing with copper 2+ and oxidizes it so that it's not around to form that zinc core. Okay, so that's essentially what we're going to be doing this week and next week. Long series of various chemical reactions and isolation, cleaning things up by filtration, by rinsing them with methanol, etc. But we're also going to be doing stoichiometry. We're going to be doing stoichiometry. So we're going to be following our copper and figuring out things like the theoretical yield of copper and the percent yield of copper, etc. So we're going to be doing stoichiometry. But we're not going to be doing stoichiometry with this guy as our starting material. We're going to start our stoichiometry with this compound. And why do you think that might be? Well, any mass before this point doesn't just have copper in it. It has copper and iron and zinc and tin and sand. So we're trying to get the cleanest starting material we can get. And the cleanest starting material we can get is this copper tetramine complex. So after you make this copper tetramine complex, you're going to clean it up using methanol so it doesn't dissolve, and then dry it. Then you'll mass it. And from this point on, you'll be doing stoichiometry. And we're going to be talking about that in processing the data. But before we leave this, let's take a really quick look at what's happening with the copper at our stoichiometric or molar ratios. This compound, the copper tetramine compound, has a 1 as its coefficient, stoichiometric coefficient, which is why we don't see it. This copper 2+ is also 1, so the first one is a 1-to-1 molar ratio. Second reaction here is also a 1-to-1 molar ratio. Just follow the coppers. The next reaction is also a 1-to-1 molar ratio. And finally, the last one, where we take the copper 2 sulfate to make copper, is also 1-to-1. So our molar ratios throughout this experiment, today and next week, are 1-to-1. And that actually helps you out a little bit with the stoichiometry and the calculations for this. So as you can see in the procedure, you're going to weigh out approximately 5 grams on a top loading balance. Okay, so you're going to put a muffin cup in there, hit tare on there, hit tare, and then put in about 5 grams, so maybe 4.85 to 5.15, somewhere in there. Okay? Then you're going to be transferring it to an Erlenmeyer flask, not a beaker, and start your reaction. Okay? So we will be talking about the exact how to do stoichiometry again in the processing the data video.